So we will switch to English for this part of the MIAI days to welcome our speaker. So I am Karthik Alahari, a research director at INRIA. And together with Xavi Alameda Pineda, we organized this series of distinguished lectures for MIAI and now the MIAI cluster. And we are honored and privileged to welcome Professor Cees Snoek, who is a professor in computer science at the University of Amsterdam, where he heads the Video and Image Sense Lab and also the interdisciplinary human-aligned Video AI Lab. He also has several other hats, for instance, being the director of 3 public-private AI research labs in Amsterdam, for example, that bring in collaborations with companies such as Qualcomm and TomTom. He's also a chief scientist at a university spin-off. He's the director of Amsterdam AI, which is another interesting collaboration between the government, academic, medical, and other organizations based around Amsterdam. And he was also the founding director of the Ellis Amsterdam unit. So Cees works on several research areas, and he's well known for his work, which spans across computer vision, multimedia, and also machine learning. So please, let's welcome Cees for his distinguished lecture.
Thank you for the warm welcome, and excuse me for switching the language to English. My conversational French is not good enough to do this talk. Yeah, I'm also scientific director of Amsterdam MIAI, so I want to compliment you with this MIAI initiative, because I know that it is not easy to get all these partners, although you are close in one initiative, and to have a joint vision to move forward. And organizing events like this, I think it's very important to meet each other and to work on that vision, because I think local communities will be very important for AI moving forward. That said, I first want to do a short survey. Who of you is not working in computer vision? Great, great. Yeah, I will try to cater for that during my talk. The picture on the first slide is my PhD student, Kien Nguyen, who did most of the work that I will be presenting. Nowadays, I'm more of like a talking head, presenting what other people have been doing. So much of this is Kien's PhD journey, so to say. And I'm going to talk about eliminating inductive bias from computer vision, and especially focusing on transformers. I want to start a long time ago. About 500 million years ago, the biological Big Bang took place, the so-called Cambrian explosion. And until then, our planet was occupied by very primitive marine species, like jellyfish and sponges and worms, and that was about it in terms of variety. But then, in a relatively short time, so we're still talking millions of years, but relatively short in the history of things, this very limited fauna was expanded to include basically the ancestors of all intelligent life on Earth. So suddenly, animal species acquired claws, tentacles, and armor. So perception started to evolve, because it became very important to be seen or to be hidden, to prevent being eaten, and also to make sure you could mate. Up until this time, it is very unclear how and why this happened, and even Darwin was puzzled by this sudden explosion of intelligent life and diversity. One of the hypotheses is that it became much more light on this planet, so visual perception started to evolve. I like this explanation. Moving forward, intelligence start to develop, and this is sort of like a blueprint of, it's not a human brain, it's a macaque brain, but it's a very close relative, and our brain looks pretty similar. And Van Essen, a very famous cognitive scientist, made sort of like a blueprint of the human brain, what it is composed of, how the different modules interact with each other. And now people focus on other certain areas, specializing in certain categories, or the what, or the where, and what have we. So this is, oh, and what is interesting here is that human vision consumes about 50% of our brain capacity. So to sense and to move in the world, 50% of our brain works on this. So it's a big problem, and it's an important problem. The human invention of written language is of a much more recent descent. So the first evidence we are aware of is sort of like clay tablets found in Mesopotamia, so the current area currently known as Iraq. And that slowly spread through multiple areas in the world, so in Egypt with the hieroglyphs, and in China and India, and what have we. And this was started around 3,500 before Christ. I get back to language, but my point here is that perception is much more fundamental to intelligence than written language. So I will get back to that point. We make a jump to the human invention of deep learning. It has many inventors, but those three people, Jan LeCun, Benjo, and Jeff Hinton, are considered sort of like the founding fathers of the discipline, and fighting for its existence, and prevailing with an idea that really turned out to work really well. Even getting 2 Nobel Prizes recently for both physics and chemistry. Unbelievable. Before deep learning, when I was a PhD student, we would work in computer vision on representations with what we call feature bias. So we would engineer the representations, and we would built in knowledge so that the representations would be robust to certain changes. A very famous one is SIFT by David Lowe. It used the fact that in the human brain, the V1 area is very sensitive to edge transitions and orientations, and this was captured in an image representations using basically gradients, and cleverly accumulating them into a vector representation, which was then forwarded in the second stage to a favorite machine learning tool in those days called support vector machine. Also from this area, very famous representation originated. So the histogram of oriented gradients, the Hock descriptor by Dalal and Trix, from India, and also Cordelia Schmid's work has contributed a lot in computer vision in these early days, so to say, before deep learning. So computer vision focused a lot on features in these days, and making those as robust as possible. And then came deep learning, and especially the convolutional neural network pioneered by Jan LeCun really became decisive. And the big step forward here is that these convnets are end-to-end, so you go from data to task that you want to solve, and the inductive biases are no longer engineered in the features, but they are engineered in the neural network architecture. And there are 3 important inductive biases in the convolutional neural network. So the first one is spatial hierarchy, And this is also inspired by the human brain, where sort of like it is postulated that in the brain we go from very low-level edge representations to higher and higher level representations until, for example, face emerges, and before that eyes and nose areas pop up. And the convolutional neural network sort of like tries to mimic this. The other aspect is location equivariance, where here we mean, or we refer to the adoption of weight-sharing mechanisms in the architecture, so that you don't have to estimate weights for every individual neuron. And last, but certainly not least, is this notion, this inductive bias of locality, where it is common wisdom in the computer vision community that pixels are close together should be treated also together, because they are very similar, and there's a reason they are more related than other pixels, so to say. So it's a strong inductive bias. All right, then things change, because in 2017, the language transformer was proposed. In the Attention is All You Need paper, I checked yesterday, it has reached 185,000 citations since. This is more than probably my entire department if we take all the professors together. So this is spectacular. And the key insight here is that this notion of attention suffices to derive input and output, in this case language, token dependencies. So they evaluated the language transformer in the task of machine translation, so how to translate an English sentence into a French sentence and vice versa. And to basically, the key idea is to have, to tokenize the sentences and to include as much context as possible in your representation learning, so that when you translate a certain sentence, you can take the full context into account to avoid ambiguities that arise between two different languages, so to say. I won't go in all the technicalities of the transformer, but this is the key equation that sort of like reflects the title of this attention mechanism is all you need. So for every token in your representation, and token here typically is a word, we create a query, a key, and a value vector by multiplying the embedding, in this case of the word, by 3 matrices that are optimized during training, and the encoder-decoder architecture that makes this happen is visualized on the right. So now we're back at language, and an architecture that was originally designed for language is now our key tool, also for doing visual intelligence and actually many other perception tasks in AI. So what people have been doing, and very successfully so, is to take the language transformer and convert it into a vision transformer. And the most successful one to date is the so-called VisionTransformer that was published in iClear 2021. And the basic idea is very simple, what they introduced. So they introduced a 16 by 16 patch token. So if we have a squared image, they would take a small patch, or they would patchify the image, and that would become the token. So the patch is sort of like the equivalent, the patch in the image is the equivalent of a word in a sentence. And the rest is all the same. They had a little bit of positional encoding and some particular token to do a classification task, but for the rest it's exactly the same as the language transformer. So this is how it works, high level. So we have an image over here. We split it into multiple patches, so they become the words in your sentence, so to say. We flatten these into a vector representation, And we also add a position embedding, an encoding of where this particular patch originated from in the original embedding, so that we have some spatial locality. And then it goes into this transformer encoder, which is simply exactly the same as what we had in this language transformer, but then only the encoder part. And because they demonstrated it for a classification task, so identifying what is visible in an image, they also had it this particular token over here, which is a extra learnable class token. That's it. Super, super simple. Now, let's look at the major inductive biases between a convnet and a vision transformer. Then what we see is that spatial hierarchy is lost in the vision transformer. So what worked really well in the convolutional neural network is being let go in the transformer, and that seems to be beneficial. So this hard-coded assumption of having this spatial hierarchy seemed like a good idea, but actually letting it go proved to be beneficial, especially, and this is the key strength of the transformer, when you learn your representation at scale, so with huge amounts of data and associated compute. This was very inspirational for the computer vision community, and many people started to transform the task they were working on, right? So a very early example was the detection transformer for localizing an object in an image by identifying a bounding box around its spatial extent, known as DETR. So they basically, for the first time, the entire community was working on object detection using convolutional neural networks, and they said, oh, wait a minute, we can also do it with transformer and transform this into a set prediction problem. So very inspirational, and what is nice is many sort of like handcrafted priors that were used in state-of-the-art architectures, including like things like non-maximum suppression and intersection over union matching, were no longer needed. So it reduced task-specific inductive priors in these object detection architecture. So that was a new insight and new finding. Now, many people transformed their spatial tasks. So this is one work by Kien early on in his PhD, where he looked into 3D object detection. So he would take a 3D bird's eye view, like you see on the left for autonomous driving like scenarios, into 3D object detection predictions. And again, all kinds of handcrafted priors that people have been proposed for this problem, you could let go and simply learn it all from data with your transformer. Here's another task many people have looked at, more multimodal, so combining vision and language. So in the sort of like convolutional network, deep learning start of things, people would encode the image with a convolutional neural network, the text with an LSTM, recurrent neural network, and then a separate fusion module would also would combine the two. Now, this is how we do it now. It is all transformer. And you can even replace it with one big transformer called a foundation model. Many papers. So I think for 4 years we have been writing, oh, look how we can convert a problem into doing it with transformers. Not only in vision, but of course also in NLP, in robotics, and we see it in many fields. The transformer is basically making us all the same. Again, all these fields do the same thing. We only play around with what is the input and some specialization things. Common lessons for the vision transformer. So it removes many of the handcrafted priors that are still quite common, and this is its biggest benefit, it scales really well. So if you feed it, or able to feed it more and more data and more compute, performance will keep on increasing, where other architectures start to saturate. So for feature-based representations, they saturate much earlier, then convnets saturate later, but the transformer will keep on going much longer even. And yeah, maybe it is surprising, but even in 2025, there are still vision tasks that profit from transformers. So I want to go a little bit deeper in one example of recent work that we proposed recently. So this is joint work with the people from the other computer vision lab in Amsterdam, more focusing on 3D computer vision, where we basically applied the lessons learned from Kien's PhD to this 3D computer vision problem of visual odometry. Now, this is a very specific task, often used in robotics, where the goal is to estimate camera position and orientation from a video sequence. So if the camera is on a robot, this helps to localize the object with respect to its environment, for example. So if you have a Mars rover and you equip it with monocular visual odometry, so from a single camera, it can determine its position. A key problem for visual odometry problems is that you have to keep track in successive frames. You have to make sure that they keep on a line so that you can reliably estimate the pose. And this is where it often breaks, because you lose the tracking and it starts to drift, and then you become uncertain about your accurate position. Now, why is this useful? So here's an example. If you have the pose, you can do very nice reconstructions with real-time rendering capabilities. So estimating the pose with visual odometry is key here. Here's another example. This is SLAM, so simultaneous localization and mapping of a robot, and visual odometry is a subtask here. So not for the mapping, but for the localization. So this is obviously very important in robotics applications, self-driving cars and what have we. State of the art, at least until 2023. Many people solving this problem, working on this problem, have adopted deep learning, but often by using deep learning in a specific module as part of a bigger system. And in that bigger system, there are often still sort of like strong inductive priors or pre-engineered components that do things like, in this case, bundle adjustment or feature matching to make sure that the camera pose estimation does not start to drift, right? This is a very recent trend. This was the best paper from CFPR 25 last week. This is from the VTG group in Oxford, a huge transformer for several 3D tasks, including also prediction of visual odometry. So this is a so-called generalist model. Our proposal is also a transformer, but not that huge, and to be a specialist for visual odometry. And I will briefly go over what we did. It has three main components. The first component is a pre-trained encoder. So we don't train the encoder ourselves. It is not that we don't want to, but it's more that we cannot because of lack of compute. But for the sake of the architect, it doesn't matter much, because we can take many of existing pre-trained encoders that people have proposed in the literature. So for every frame comes out a token embedding. Then comes, and that is where our key contribution is in the decoder. So we add the camera embedding to the token embedding, and this is also embedding we want to optimize during training. And then we have two attention phases, so to say. So we interleave temporal attention with spatial attention. So the temporal attention is to make sure that we track things in successive frames accurately to prevent the drift, and the spatial attention makes sure that we also add the region into account. And this allows also to capture long-term dependencies, which are kind of crucial when you're doing pose estimation over multiple video frames. Okay, then comes the third part, where we start to define the loss. So we output rotation vectors, and those need to be still projected to the closest valid rotation matrix. So that's being done, together with a geodesic loss between the predicted rotation and the ground truth that we have during training. And then the translation loss goes, the relative translation is used directly as output from the decoder, and there we simply use an L1 loss. And we combine those two losses for the final results. Here you see some attention maps visualized. So in this case, the red square is the query, and what you can see in successive video frames is that it really attends to the related image regions. And it also nicely resembles what people did in the feature engineering phase to work with key points and identify important points in the image, for example, by looking at edges locally that were very salient. And now this sort of comes back, but by learning. So we were at the right track, but we just did not have the tools to learn it well. One table which results, which I think are interesting, not so much the numbers, but the fact that this VOT that we propose is competitive with state-of-the-art, without relying on these manual components, these inductive priors. So we no longer need bundle adjustment, we don't need camera parameters. So this deep patch visual odometry is still pretty strong. It also outperforms many of these foundation model approaches that are generalist, but are maybe not so good in this specific task. So this is, I think, interesting, especially because the transformer has a few interesting properties. So the first one, that we can scale this, right? So we can add more and more data, we can add more and more parameters, and that will assure that performance will go up. In this case, performance goes down because we are maximizing the absolute translation error and the absolute rotation error. So as you see that if we add more and more data during training, on the one on the left over here, so more and more data is added, results go down nicely, which is the expected behavior for both metrics. It starts to go up in the beginning. This is expected behavior, because with very limited data it starts to overfit. So then results get worse. Here we see another plot where we simply add more and more of the decoder blocks in the transformer, and both metrics also nicely go down. So ideally we would have scaled this up even further, but we don't have the compute to do so, but the trend is clear. Nicest is this one, because we no longer need tricks like bundle adjustment or auxiliary optical flow computation, camera parameter estimation, what have we. Our approach is much, much faster than what is available in the literature. And I think this is also in the end what you want, because at inference time, you want to do all this visual odometry computation, and you don't want to have, you don't want to bring a huge GPU farm when you go to Mars. right? So if your robot can be much more flexible when it's needs less compute. So this is a nice property. So we again see the common lesson that hold for VisionTransformers, also confirmed in this problem. We remove the need for handcrafted priors, and we scale well. Okay, so all great. In a way, not so surprising, because we have seen this for many other problems in the past as well. But Kien started to ask himself, I think, a very interesting question. So, can we increase the inductive bias further? So, the VIT has basically two inductive biases left, so this location equivariance, so this weight sharing is much less actually already than in ConvNet, but it's still there. And then it has this notion of locality, which is captured by this 16 by 16 patch encoding, and also by the positional embedding that is added manually, sort of like also like a feature that is added in the representation. So now we're getting to eliminating this locality bias in vision transformers. And this is joint work with our friends at FAIR in California, who also nicely provided compute to execute this investigation. And this was published in iClear last May. So, the hypothesis is as follows. If a transformer with pixels instead of tokens or patch tokens can work just as well compared to a regular VIT or a ConvNet, then locality is maybe not that fundamental for computer vision. So what Kien did, he came up with a very simple vision transformer where he simply removed all locality priors. So instead of giving it a patch, he gives it a pixel, or you could also say a 1 by 1 a patch, so that becomes your token. And rather than injecting this, what is common sine-cosine positional encoding, he learned the positional encoding as part of the training, so it is not injected a priori. And we will demonstrate this on both discriminative and generative problems. Pixel transformers have a few appealing properties, also not so nice properties, but a few are nice. First, the model is much more versatile because it can naturally handle variable image sizes. So you're no longer restricted to fixing all your input to a fixed resolution. It reduces the vocabulary size of your input tokens considerably. So where in a normal vision transformer with a patch of size p, you have 2 to the 256, so the number of values in RGB times the power of 3 times this patch size, and it can be reduced to 256 to the power of 3. So that is advantageous. Of course, it is computationally much more demanding, but there is actually a growing investigation, and more works are appearing where people show that this sequence length of transformer can be expanded, and we are sort of getting there, because if you take a standard 224 by 224 crop from an ImageNet classification task, you're dealing with about 50,000 pixels. So that's not even that long of a context. But computationally, it will never be. It will never beat the token one, right? So that was also not the intent. We are looking into what if we do this? What is the impact? So we did 3 empirical studies, so to not be restricted to one particular setting. So we consider supervised learning, where we do traditional classification tasks on CFAR 100 and also on ImageNet, but with smaller resolution images. We do fine-grained classification on a dataset called Oxford Flower, where the task is to identify different types of flowers, which is much more difficult than identifying, distinguishing a hammer from a flamingo, for example, what you have in ImageNet. And we also did a task of depth estimation in image data, so slightly different problem with larger resolution. We also looked at self-supervised learning in the masked autoencoding formalism, and last but not least, we looked at diffusion models for image generation, also with this pixel representation. So let's look into supervised learning first. So now I will show some slides with numbers, but no need to look too much into the numbers. What is interesting here is that this row indicates the normal VIT with the patch token. So here we took 2 by 2 as the patch size, and we compare it with a VIT with just a 1 by 1 patch size, so just a single pixel. And what we see for CFAR 100 here, that the results are slightly better. This is a tiny VIT, and this is a small VIT, and we see the same behavior. This is the result for ImageNet, and again, learning from pixels is better than learning from larger patches. And it also seems that the larger the capacity of your transformer, the larger the benefit if you can afford the computation. So this suggests that a VIT with pixel tokens potentially learns new data-driven patterns that are not captured by sticking to this inductive prior of locality with patch tokens. We see the same results for fine-grained and depth images. So again, the 1 by 1 pixel outperforms the token, the patch-based token approach. So this tells us that transformers without locality injected in them will learn this themselves from data. So you don't longer need to assume two-dimensional image grid as input. The transformer figures it out. There is some evidence here. So this is a visualization of the attention layers, early layers of the pixel tokens, and you see that figure ground segmentation emerges. And this is already in the early layers. So it starts to group the pixels by itself. Here's another plot where I think this is interesting because this shows the mean attention distance between pixels in your image for the pixel token and the patch token. And what we see here is that here the distance is, in this area, the distance is low. So that means that it really focuses on areas that are very nearby for where to attend, right? So the attention mechanism really says nearby is where the interesting things happen. So already in the early layers, it starts to focus on what is nearby. So this area over here. So that is the behavior you want, basically. Now, then we looked into self-supervised learning. So here we used self-supervised learning with a method called masked autoencoding. So for the people familiar with BERT language model, this is basically the same trick. So rather than masking a word in a sentence, here we mask a patch in an image. So let me explain very briefly. So we have an input image that we mask randomly, and then all the unmasked patches go into an encoder, comes out some embedding. Then we put in back the masked regions, and then the task becomes for the decoder to reconstruct this masked vector as good as possible to get the target image. And so all you need is an image, you add some mask, and you have a self-supervision mechanism that it can learn to optimize the encoder as good as possible. Once the training is done, you throw away the decoder, and you only keep the encoder that is then optimized to do this as good as possible, and that you can fine-tune with labels for the task of interest. And here we did that with CFAR 100 classification task, and this came out. So this is without self-supervised pre-training, but doing the normal way. This is with self-supervised pre-training, so it works as expected. And again, the pixel tokens outperform the patch tokens. Doesn't matter whether it's tiny or small, a backbone, we see the same behavior. Third study, this is the last one, we looked at image generation. So in image generation, people have looked a lot into generative adversarial networks, often with convolutional neural network architectures. And in diffusion models, people typically looked at UNet architectures to convert from noise to a realistic image. But of course, also this problem can be transformed. Unfortunately, it was not us, but there was another paper at ICSV in 2023 by William Peebles and Sanching Xi from Berkeley and NYU, who proposed the diffusion transformer. I will not go into too much detail, but basically they have the same trick. So essentially they also use a patchification in their architecture. The main difference with the normal transformer here is that they operate on the latent representation of the image and the patch tokens rather than the full image. And here we can also simply replace the patch token with our pixel token approach. And again, the pixel token shows better generation quality compared to all these different metrics that people use to assess how good the generated image is. And we also see a positive effect in scaling, so training from 400 to 1400 epochs, for example, and we remain consistent. I would not say it's a huge difference, but it is consistent also for the image generation problem. Some eye candy, so I would also say that it's so on the left is the one with 2x2 patches, and on the right is with pixel tokens. So it can do this as well. That brings me to the end of my talk. I would like to conclude that, well, vision transformers are great. They eliminate many task-specific inductive biases that we have in computer vision. And I think the point I would like to make in this talk is that vision transformers have inductive biases too. And the one that we have all believed, myself included, to be super important, the one of locality, remains very practical to save compute, but it is not fundamental. So we don't need it if we would have the resources or the right representation available. So that implies that there is plenty of room at the bottom of the architecture to look deeper into representations with pixels and maybe with recurrent architectures or other new to be developed architecture, because every architecture has a life cycle, and at some point the one of the transformer will also end. And with that encouragement, I would like to close my talk. Thank you.
for questions.
So thank you for your talk. I have a question about your pixel transformer. Intuitively, I would say if I make the analogy with a language transformer, it would be like taking only the letter and not the word token. And at least for me, intuitively, I wouldn't bet on that strategy. So what's your intuition about why it works for images?
So it's not practical, right? I mean, people will not start to use this now, tomorrow, in their daily practice when they work with VisionTransformers. But I think, so the opening statement of our paper was this: we do not propose a new method, right? It is really about the finding of this notion of locality that is not crucial. It is important for keeping the computation manageable, but from a representation perspective, it is not crucial. Okay. So I would say it will not change your daily operations as you're working with VisionTransformers. Keep doing what you are doing, I would say. But if you're interested in representations and architectures, then maybe there is room for a successor of the transformer. And the transformer was made for language, and we have abused it to make it suitable for vision. But I think that is the wrong tactic.
Okay, thank you.
Thank you for the very nice presentation. I do have two questions, and the first one is on this special hierarchy inductive bias. Yeah. It is not clear to me that this is not captured by transformers. If I take the analogy with language, then there is structure in language and syntactic dependencies, semantic dependencies, and it is captured via the different layers, because you first get some representations of pairs of tokens, then of pairs of tokens, and so on and so forth. So it is assumed that there is that the underlying structure is captured by this mechanism.
I guess we can argue, maybe to make it a little bit more specific, is that this multi-scale architecture is lost in the transformer. So which is very explicit in the convolution neural network, is much less explicit in the transformer.
Okay. And the second question is on this locality result. You have on one of your slides that you have learnable positional encoding. So, and so I was wondering, in a way, even the locality learned by the transformer, because you provided the ability to do so. Yes. And finally, locality is still important, but it is.
So maybe I should rephrase it a little bit. Locality is still emerges, but we don't have to explicitly inject it a priori. I think that is the right formulation. Yeah, thank you.
We have another.
Yeah, thank you for your talk. I've got a question, so maybe it's a bit naive, so just forgive me if this is the case. It's about your this notion of inductive bias. I feel that it encompasses a wide variety of stuff. You've got modeling knowledge that come from the scientist.
Yes.
You've got handcrafted priors, where prior is understood the old-fashioned Bayesian way, where you try to put some knowledge on top of your model. And there are also pain in the neck issues, such as parametric tuning, about the camera, whatever. So it's really, really wide.
Yes.
And for some of them, it would be really great to get rid of them. Some others, well, it's possible, essentially, if we've got more data to extract, to get the knowledge. But some of them may be still necessary, essentially, when you're performing a modeling test as a scientist. And I was wondering about if those inductive bias were really well classified and kind of prioritized, because, as I said, some may remain of interest, while others should be gotten rid of as soon as possible. not a computer vision perspective. I mean,
Yeah. So I mean, the goal of the talk is not to be against inductive biases. I think there are many applications conceivable where inductive biases are still very important because you don't have the amount of data that we're talking about, or don't want to use the amount of data, or you want to be explainable, right? There are many reasons why you pick a certain tactic. I think the point here is in computer vision today, this is sort of like the leading mantra, right? It is we take data, we take a transformer, and we solve our problem. The bigger the transformer, the better, right? And the more data, yeah, I think this was sort of like an interesting study to see. Okay, we have this notion of locality, and how explicit do you need to make it a priori? And it turns out you can relax it quite a bit, and that is, I think, is inspirational for new architectures that reconsider representation learning from pixels with a new approach. Does that answer your question?
Yeah, perfectly. Thank you.
Thank you.
It seems that there's a question online. Yes.
Yeah, this is a good question. I looked this up in the paper myself also yesterday evening because I expect it's not mentioned in the paper. So I don't have this answer. Kien has to answer this, but the fact that it's not in the paper maybe says it all. So it is really not a competitor for in terms of compute for patch, and the only way we could do this study is because we collaborated with our colleagues at Meta, because they have the compute resources to sort of like do this.
Yeah, thank you for your talk. Very interesting. I'm not an expert in computer vision, but I know that when we talk about inductive bias and we think about how children have this inductive bias in the way they perceive a visual scene, to the best of my knowledge, they talk about inductive bias in terms of shape, like they prefer, they generalize to when they have to learn a new object or the noun of a new object, they generalize to something that have the same shape. And apparently you find in the early stages of the processing some kind of search for shape invariance, or I don't know how to call it.
Yes.
Have you considered to correlate that with some fundamental knowledge on human perception?
Yeah, so actually we did a experiment to analyze, because this is also a debate in vision, whether architectures are like shape biased or texture biased. ConvNet is known to be much more texture biased than shape biased. The human brain is known to be much more shape biased than texture biased. And when we compare the 2x2 patch with the pixel token, so to say, we found that actually we are more shape biased than the regular patch token. So I think that, yeah, so it's not conclusive, but it's sort of like interesting.
Thank you. Great.
Any more questions? So I had one maybe. So it feels like, with the pixel and the patch level, so you're kind of going between two sort of extremes. I don't know if you've looked at something sort of intermediate where maybe there's a hybrid of the two approaches.
Not a hybrid, but we did look at, maybe I have that. We did look at different patch sizes and also why people did not do this earlier. So the plot in the left, I think, is what people looked at in the VisionTransformer paper, but there they kept the sequence length fixed. So if you keep the sequence length fixed and you make the patches smaller, you will see that the smaller your patch becomes, the worse performance will be. So that's why they opted for the 16 by 16 patch size. The plot on the right fixes the input size, so your image size. And then the story becomes a little bit more different, because if you fix the input size, then reducing the patch size is always helpful. So it is all about this implies that the vision transformer mainly benefits from a high resolution input image, and less so from the patch. The amount of information you put in is the decisive factor.
Thank you. Let's see if there's one last question. Ah, there's one there, Sophie.
Thank you for the presentation. I'm just wondering if the pixel transformers are getting more popular along the great amount of images that are generated or used by big companies because they prefer to scale for performance.
I think they are not popular at all. I also don't think they will become popular soon, because it's computationally, it doesn't make sense. Right? So that's not, I'm not advocating you should all switch to pixel transformers. I think I'm advocating you should work on new architectures that take the pixel more into account.
Okay, so with that, okay, maybe one last.
Thank you. That was really interesting. So I'm wondering about this absence of locality input, and how does this fit with the current GNN evolutions, where you kind of try to assume even sometimes some long distance relationship between pixels? So how can you comment on that?
So you said GNN?
Yes.
So graph neural networks?
Yes.
I haven't thought about that, but maybe, yeah, that could maybe be an interesting avenue to connect the graph with pixels. But my first hunch would be that recurrent architectures deserve attention in this respect, because they can handle extreme context length much better than transformers can, because they don't have the quadratic complexity. But yeah, graph neural networks I haven't thought of, but maybe that also warrants, or maybe you can look at it when we compare notes.
Okay, so on that note, let's thank Kees again for this amazing, distinguished lecture.
Ok, donc après cette présentation effectivement très intéressante, je vous propose de faire un petit jeu, un petit quiz, un mini-quiz qui a été préparé par l'équipe de MIAI et qui porte sur MIAI en fait. Donc ça sera assez rapide et le but du jeu c'est de répondre à 17 questions. Voilà, donc il faut vous connecter. C'est Jana qui est en haut qui a organisé ce quiz pardon, et qui va gérer tout cela. Viendra à la fin pour décerner des prix. Il y aura des goodies, je crois, pour tout le monde. Il y aura des prix pour plusieurs personnes. Dans les prix, il y a une bouteille de champagne. Et puis, il y a un super prix pour le premier gagnant. C'est une présentation de 10 minutes lors des prochains MIAI Meetings pour le premier gagnant. Le deuxième gagnant aura droit à 5 minutes de présentation. Le troisième gagnant, non, je plaisante, mais c'est vrai pour le premier gagnant. Voilà. Donc, donc vous aurez 3 minutes chacun, les gars. Vous arrivez à vous connecter, oui? Oui. Donc, je crois qu'il faut remplir, il faut donner votre prénom lorsque c'est demandé, le numéro du quiz. Oui, on attend que tout le monde soit connecté avant de démarrer le quiz, qui sera en temps fini. Et il importe à la fois d'être correct dans ses réponses et assez rapide. Un petit peu, ouais. Mais pas trop, ça va. Est-ce que toutes les personnes qui voulaient se connecter sont connectées? Thomas, tu t'en sors? Non? Oui. On te laisse encore 2 minutes, allez, vas-y. C'est bon, tout le monde, toutes les personnes qui souhaitaient se connecter sont connectées? Ok, ben, je pense qu'on peut démarrer. Et je ne sais pas à combien de temps ils ont droit. Je peux voir en direct le classement des 3 premiers. Il y a une équipe qui est impressionnante. Si vous ne voulez pas présenter lors des prochains MIAI Days, ralentissez. Hein. Ah, le classement a changé. C'est bon, là, c'est OK? OK. Est-ce que tu descends pour la remise des prix? OK, donc nous avons le classement. Que vous voyez affiché, en fait, oui, effectivement. Alors, je ne sais pas qui est Sherlock from Vienne, mais c'est un participant qui est arrivé un petit peu après et qui a réussi à faire très vite. Qui est Sherlock from Vienne? Ah, on va peut-être savoir. Donc, vous pouvez descendre sur la scène? Sandrine Voros et Thomas, je ne sais pas qui est le Thomas. Ah, les deux. Ah, mais venez. Et puis, Laurent Girin? Ah, en ligne.
Du coup, la troisième personne, s'il est en ligne, on doit faire en sorte de savoir. Ah, il y a quelqu'un qui l'a dépassé. Alors, Laurent, elle est passée 4e place. Et du coup, il y a M. Est-ce qu'il est dans la salle? Bah, parfait.
C'est pas figé, en fait,
Bah oui, normalement, c'est figé.
Non, c'est figé, ok. Donc, c'est M le troisième. Et M, c'est... Ok. Mais montez sur scène, en fait.
Je pense qu'on peut les applaudir. Félicitations. Merci beaucoup. Est-ce que c'était difficile?
Scientifiquement parlant, c'était notre plus grand fait d'armes.
Bah, du coup, en fait, nous, on garde ça et après, on va vous contacter aussi pour la participation au MIAI Meeting. Merci beaucoup.
Bon. Ok, donc ce quiz clôt la session de ce matin, donc je vous propose qu'on passe au buffet, puis nous reprenons cet après-midi avec les présentations scientifiques en partie.
Qui sont dans la salle, mais qui